So now we move over to small world networks. This is again a very interesting set of networks that were proposed by Watts and Strogatz in 1998, and they suggested that you start with a regular network and you rewire it. So a regular network is what? They call it a regular lattice. It's a regular graph. The property is that every node is connected to 2k nodes. Right. So think of this for simplicity as people sitting around a table, and everybody knows k people to either side. So every person sitting at the table knows 3 people to her right and 3 people to her left. So and so on. So you can have these kinds of and so here k is 3 and every node has exactly a degree of 2 into k, 2 into 3, 6. And when you have this, you have short path lengths, that is fine, but you have very regular structure. What Watts and Strogatz suggested was that you now start rewiring this regular table, meaning you sever some links that are immediate, that are adjacent to you, and connect them across the table. How do you do that? So what they suggested was, let us do this with the probability p. So if I have p equal to 0, I have a regular lattice, I do not rewire any of the edges in the lattice. But if I have p equals 1, I am going to rewire everything and I probably end up with like a network with very little structure. It is going to be different from your random networks. Maybe that is something that you can try and test out, how different are they, right. But then you also have a zone in between p equal to 0 and p equal to 1, where you have some part rewiring, where you have very interesting properties. What are they? We will come to in a moment. So just to recap again, you have 3 different regular lattices on your screen. So in the first one, k equals 1, which means every node has a degree of exactly 2. Here k equals 3, so every node has a degree of exactly 6. Here k equals 4, where basically every node is connected to every other node. There are only 8 other nodes in the graph. There are a total of 9 nodes. So every node is connected to all the 8 remaining nodes. So what Watts and Strogatz found was, for a large region between p equal to 0 and p equal to 1, you find 2 interesting features which they called small world features. We will see why that word, the phrase small world makes sense. What you observe are high clustering and low path lengths. So low path lengths is something that we always want, because whenever you try to model real world networks, you want the model to capture this real world feature of low path lengths. But here you also have high clustering. Are real world networks clustered? And well, you must be very familiar with the phrase small world, right? So when you go to some place and you meet a bunch of people, you realize that, oh, I already know this person from some other walk of life, which is basically that A knows B, B knows C, but then A also knows C. So what is this? If you recall, when we looked at clustering coefficients, we said this is what a cluster is. This is actually a triad, but when A knows B and B knows C, what is the probability that A knows C? How often does A know C when A knows B and B knows C, right? So this interesting feature is what is we call small world in the real world, and this is what Watts and Strogatz called as a small world network in this context. What did they say? They say that they showed that for a large region between p equal to 0, where you have no rewiring, to p equal to 1, where you have completely random rewiring, completely a random network in some sense, you have a zone where you have networks like this, where you have small world characteristics. What are these small world characteristics? You have high clustering and low path lengths, and this is very interesting because this captures a very important feature of real world networks. So in both ER random graphs and small world networks, the connectivity distribution peaks at an average value and then decays exponentially, and so these networks are also called as exponential networks, and they are also called homogeneous networks because no node is very different from the other nodes. Yes, there are differences, there are good differences in the number of edges that they have, but it's still relatively low compared to what you would see in other kinds of networks, right. For the same for the same density or the number of nodes and edges, you could have very skewed degree distributions in certain cases, and that is exactly not what you see in the case of either ER or WS or Watts Strogatz small world networks. So, what did Watts and Strogatz do? How did they study these networks, right? So, they had to answer this very interesting question. So, they had to show what are the small world characteristics. So, they showed that these networks, a bunch of networks that they studied, basically they studied a film actor network again. I'll ask you to recall the Bacon number, Kevin Bacon game that we were talking about a few classes ago. And then there is a power grid network and a C. elegans, which is a very famous worm model organism used in biology. C. elegans neural network, which is a relatively small network with only close to less than 300 neurons. So, how do I make statements such as L is of the order of random world networks, but C is much greater than random world networks? Let me first draw your attention to the table. So, this is a table from the paper by Watts and Strogatz. They show that L actual is of the order of L random, but C actual is much greater in the real networks compared to random networks. So, you have order of magnitude variation in the clustering coefficient. How did they go about doing this? I think I already gave you a hint when we just talked about random networks a few minutes ago, where we were looking at generating ensembles of GNP graphs and so on and making comparisons. And that is exactly what you do here. I have a value of n and I have a value of average degree here, which is given as k, right. So, you can now therefore figure out what is the total number of edges in the network. Now, if you were to generate networks, GNM networks with n number of nodes and a given number of edges corresponding to the average degree, you will see that you can generate an ensemble of networks. You generate that ensemble of networks and then you make a comparison, you find that this is the rough value you get for clustering coefficient in this ensemble. So, in the film actor network, the clustering coefficient is as low as 0.00027 for the random case, meaning if you generated an ensemble of networks that are sized comparable to the film actor network, you see that their clustering coefficient is 10 to the minus 4, very low. Whereas, in the real network has a clustering coefficient of 0.8. So, if two actors, if A has acted with B and B has acted with C, there is an 80% probability that A has acted with C. So, that is how clustered these film actor networks are. I hope you are getting this point. So, just to repeat, how did they do the experiment? They have a bunch of real networks. Now, you generate ensembles of random networks that are comparable to these real networks. We want to be able to compare them and they should be comparable in terms of the size and density and so on at least, right, that is the minimum that we would have. So, when you generate similar looking networks, so similar sized networks, similarly dense networks, an ensemble of them and compute certain properties such as characteristic path length and clustering coefficient and so on, you find that the characteristic path length of the real network is not very different from what you see in the random ensemble, but the clustering coefficient is much different. Okay. And the table legend below shows you further details on how these networks were constructed. So, this is something that you can try out and understand, and this is a very old study. You can see how whether the small world behavior has been retained in these networks and so on. So, what is small world behavior again? Small world essentially tries to capture two different behaviors. One is a low characteristic path length, comparable characteristic path length to random networks, and second one is high clustering. essentially we started off with random networks where only one feature of real world networks was being captured, which was low path lengths. Now we have a second feature of real world networks being captured, which is high clustering, because because in the real world you always find a lot of clustering, be it in social networks or be it in protein interaction networks or whatever real world network you look at, you do see a high amount of clustering, and this is now captured by the Watts Strogatz small world network model. But then there are still features of real world networks that aren't captured. There is this very nice book called 6 Degrees written by Duncan Watts, which talks about very many real world networks, including how Toyota's spare part network and so on is a sort of connected small world network, and how that works to the advantage in various real world scenarios and things like that. So, I invite those of you who are interested in this kind of a topic to skim through this book, because it will give you very interesting real world perspectives into how small world networks can be found in various real world scenarios and so on. So, coming back, I was telling you that our list of real world network properties included low path lengths and high clustering, which are both taken care of by small world networks. But it turns out that small world networks do not capture one very important aspect of real world networks, which is the degree distribution itself. The degree distribution of real world networks is very intriguing, as I will show you shortly.